Swayam Prabha. Digital India. Educated India.
Hello everyone. So today we will start with another important topic on mechanical characteristics of textile material, which is elastic recovery. Elastic recovery is a characteristics which determine the recovery characteristics of a material. Like for any garment or any technical textile, after application of load, the material should come back to its original position, original shape and size. So in apparel, we have observed that some portion of our body apply higher stretch, and for repeated stretching, the material results a permanent deformation. So the permanent deformation or recovery characteristics is expressed by the term elastic recovery. So let us see one material. So this is initial length of the material, yarn, fabric, it's AB. Now it has been stretched to a certain extent, then the total distance after the stretch will be BC. BC is the distance, it is the total stretch, and BD is the total, this is the total elongation, and then after relaxation, after releasing the load, the material has come back to the position C. So originally the BD is the extension and original gauge length is AB. So permanent deformation here is CD. CD is the permanent deformation. So AB is original length, CD is elastic extension. That means after deformation, the material has come back to not to its original position B, but it has reached to C portion, that is CD is the elastic extension which has been recovered. BD is total extension that I have mentioned, and BC is the permanent set, that means permanent deformation. Okay. Now if we try to see the elastic recovery is expressed by the elastic extension which has been recovered, that is CD, divided by total extension, that is BD. CD by BD is the elastic recovery. Now we can consider a material which is, say, perfectly elastic material. So perfectly elastic material means the material will recover completely where BC is 0. That means there is no permanent deformation. So when BC is 0, that means BD will be equal to CD. That's the condition, and in that case elastic recovery will be 1, that is 100% recovery. And for perfectly plastic material, that means there is no recovery. In that case CD will be 0. CD is 0, so elastic recovery in that case will be 0. So let us see the animation once again. So material is being extended, AB is the original length. So up to D point we are extending, then again we are relaxing, and it has come back to the C position, and we can calculate the elastic recovery. Okay. So it is the property of a material which tends to recover to its original size and shape. So any elastic material will try to recover its shape. That's important for any application. Suppose a garment like a trouser, at the knee portion of trouser there is a stretch, and that the stretch it repeats, and after certain use the knee portion gets permanent deformation. That phenomena is called bagging effect. Okay. This we have already discussed. AB is the original length, okay, and BC here in this picture, BC is the total stretch, and then after releasing of the stretch it has recovered up to the point T. Now here the elastic recovery here, as we have discussed, CD, this recovered distance by total extension. Elastic recovery, it will be, as per the picture, it will be elastic recovery will be CD by, here it will be BC. CD by BC, it will not be BD here, because the elastic recovery is the BD is the plastic deformation. So it's not that CD by total deformation. Okay, this will be BC, total deformation. And for perfectly elastic material, that CD, this will not be D, it will be C. So it will be basically BC. For plastic perfectly elastic material, BC will be CD. So it is coming back perfectly. So elastic recovery is 1, and for perfectly plastic material, so there is no recovery. So this C and D will coincide. So CD will be 0. So bagging effect dimensional stability of garment. So these are the different types of effects which we get from the garment, and also this is very important for technical textiles where constant or repeated loading takes place, particularly geotextiles where constant loading takes place. So there this permanent deformation changes the characteristics of the material. So time dependent effect, which is called the creep effect. Suppose in a load elongation behavior, we have seen with the increase in load, if we increase the load, the material gets elongated. Now for a particular load, so suppose for a particular load, this load, the elongation is supposed to be, this is the elongation. So we are, so this is the load X. We are applying here X load or elongation. So this is a Y load. Suppose this is a Y load is Y and elongation is X. So if we apply load Y, suppose we are applying load Y here, then with that load, as per this curve, this will get extended, and extension will be, this extension should be around X. As per this curve, it should be X. But so if we apply a constant load here and we leave it for certain time, so this is a constant load here, so W load we have applied and we have left it that stressed condition for certain time, say T1. What will happen? The elongation at this time, as per the curve, say elongation for load Y, W, maybe we can consider say load Y. So in that case, elongation should be, deformation should be this X. But effectively it has been observed that if we keep the load for long time, there will be slow extension. This is called, this effect is called creep effect, and this is happened due to the gradual molecular orientation and molecular sliding. And if we keep at that stressed condition for long time, the load on the material, so at that stressed condition, suppose we are keeping, say load is say X, load is X, and that load in that stressed condition will get reduced gradually with the time. So one thing first is that we are keeping the load constant, keeping it for long time, and we are observing that there is a gradual increase in deformation. This phenomenon is called creep effect. And if we keep a material under stressed condition for long time, the load exerted by the material will gradually reduce, and that effect is known as stress relaxation. Okay, and after that deformation, if we release the load, if we remove the load, the material will try to come back, but it will not come back to its original position. There will be a permanent deformation which is due to the molecular sliding. Even it has been observed, suppose this is a load elongation curve and this is elongation load. So in normal case, if we leave the material after stretching within the Hooke's region, this is the Hooke's region, straight line, say OA is the Hooke's region. Within the Hooke's region, after stretching, if we release the material, theoretically it should come back. That means we are loading it by L and then up to L loading, and then we relax it, it should come back because of the hooks. It is hooks in the within the Hooke's region. Okay, but suppose we are keeping this load here L, which is within the Hooke's region. Still, what we will find? We will find there will be a creep effect, and after releasing this load L, in normal testing it is coming back, but after creep effect there will be again be a permanent deformation. So this deformation is due to the creep effect, molecular sliding, and that happens with the lower load also. So if we keep a certain constant load on a material, particularly viscoelastic material, this is on viscoelastic material, and there will be permanent deformation. Now try to solve a numerical on elastic recovery. Let us see. A yarn specimen of 400 millimeters. So this is the yarn specimen A and B is the yarn specimen. So length is 400 millimeter. Okay, and extend 10%. 10%, that means we are extending it to 4 millimeter. 40 millimeter we are extending. This is the BC. BC is 40 millimeter. We are extending it to 40 millimeter and loaded by 600 centimeter. The length of the specimen after removal of the load is found to be 405. So there is 405 D point. So BD is, this is 405, will be 5. AD is 405. So this is 5 is the BD, is the permanent deformation is 5, and elastic recovery will be 40 minus 5, 35 is the elastic recovery, and if we take the ratio we will get the elastic recovery of the yarn. Now let us see. So elastic extension is 10%, load is 60 centinewton. This value will not be required because we are trying to calculate the percent recovery. So load is not required, only the length parameters will be required. So specimen length after removal of load is 405. So there will be original length, extended length will be original length plus 10% of the original length. So it will be 440 is the extended length, and then when it recovers, it has become 405. So elastic extension divided by total extension is the, and if we want to get the percent elastic recovery, then multiplied by 100. So 40 is the total extension, and elastic extension equal to extended length minus length of specimen after removal of load. So 440 was the extended length, and the length after removal of load is 405. So 35 millimeter is the elastic extension, and if we calculate the percent on the total extension, so 35 by 40 is 87.5%. Next numerical is a yarn specimen of 250 mm extends by 5%, and load will not be required, load value is not required because we want to calculate elastic recovery. So 5%, so 5% of 250 is the elastic total extent. This is extension, total extension is 5% of 250. So that will calculate. So initially it's a 250 total length after extension equal to 250 is the length and extension, 5% of this is the extension. So it will be 12.5. So 262.5 is the extended length, and after recovery the length is 254. So total elastic recovery would be 262.5 minus the recovered after recovery length 254. So it will be 8.5 millimeter. So this is the elastic recovery. So recovery of, not, it is not the basically elastic, it's a recovered length recovered. Sorry, this is the, it's not the elastic recovery, this is the length recovered. Length recovered. So length recovered is this 8.5 and extension is 12.5. So if we calculate the ratio elastic recovery percent, it will be 8.5 length recovered by total extension is 12.5 due to loading. It will be 68.68%. Okay, so these are the steps. Original length of the specimen 250, extension 5%. So and final length is after recovery is 254, so extended length will be 262 millimeter and total extension will be 12.5 millimeter and elastic extension is the extended length minus 5 length, final length, which becomes 8.5, and if we take the percent, we will get 68%. Okay. Next numerical, similar numerical is a yarn specimen of original length 80 millimeter. So this is the yarn specimen of original length AB is 80 millimeter. This is stretched to a length C, stretched to a length, so of 125 millimeter. We are stretching to, and after removal of load, the length becomes 99 millimeter. So this is stretched length, and here D so BD after removal of load 99 millimeter. Okay, this is the and elastic recovery we have to calculate. So stretched length, so length recovered will be 125 minus 99 equal to 26. Okay, length and total stretch will be BC. So total equal to 125 minus 80, it will become 45. So 45 is the total stretch and recovered length recovered is 26 millimeter or millimeter. So elastic recovery percent will be 26 divided by 45 multiplied by 100. It will become 57.7% recovered. So elastic recovery is 57.7%. You can see elastic recovery is 57.7%. Next, similar numerical, a yarn specimen of 3 millimeter extended by 5%, that is, it will become 315 when loaded with 5%, that is, it becomes 315 millimeter. The length of the specimen after removal of load is found to be 304. The elastic recovery percent, the similar way we can calculate. So the elastic extension will be 315, that is the extended length, minus 304 load, the length after removal of load, and total extension 305%, that is 15 total extension, 315 minus 300, so it will become elastic recovery, and percent if we calculate it will be 73.33%. Elastic recovery can be expressed in fraction also, and also by the percent. Now we'll discuss different factors which affect the tensile result. So for a certain, now here the situation is that we have a certain material, okay, a particular yarn we have, and it's tested in tensile tester, and the result can be changed. For same material, one can change result. So there are by changing different factors. If we take the different material, the test result will be different, but same material, the result can be changed. First, if we change the specimen length, that means gauge length. So this is material and tested in a gauge length. L1 is the gauge length. Okay, this is the gauge length. Another material, so another, first we have tested same material, we have tested in a same machine, but what we have done here, L2 length, gauge length is L2. Now we have to see whether this two results will be similar or same or not, considering we are using the same material. Okay. Now let us see if we change the specimen length. Here the materials we are considering here, it's not the uniformity. For any uniform material, 100% uniform, there is no non-uniformity. If we change the gauge length, we should get exactly same strength. But for textile material, we know the materials are uneven in nature. This is uneven. Okay. And if we plot the strength of at different points, this is the length, total length of the yarn. Here you imaginary strength point we are now trying to plot. So this is the mean strength of the yarn. Now for particular point, say we have say n number of points at different imaginary points we have considered. Suppose we are able to measure the strength at each and every point somehow. At different point we have got the strength value, and that if we try to plot, these are the strength. This is the strength and this is along the length. Along the length at different point we are trying to get the strength. Now this is total length of the yarn is L. Total length of the yarn is L. Now what we are now trying to see, if we test the yarn as with a gauge length L, complete longer, suppose the L is equal to say 1 meter length. So if we test the yarn in a tensile tester with gauge length, so jaw 1, jaw 2, if it is the say 1 meter length, when we test, the strength of this portion will be the strength of the weakest point. So here the weakest, suppose S1, S2, S3, S4 like this. So S4 is the weakest among all these different lowest point peaks. So the breaking strength is the load to break at its weakest point. So if we take the gauge length as 1 meter, then the strength will be S4. Okay. Now let us see, we are taking the gauge length as 50 mm. We are dividing into two parts. So two parts. So one is then 50 centimeter. So 50 centimeter, half. J1, J2. We are dividing into equal two parts. This is the two parts. We have tested say L1 and L2. So for L1, when we are testing L1 equal to L2, the part 1 and part 2, the portion part 1 and portion 2. When we test portion 1, the strength will be, that means weakest along this length, weakest point is S4 again. So it will be S4. And when we test portion 2, left hand side, this portion, then the strength of this portion will be the weakest among the weak points. So here weakest point is S3. So for part 2 it will be S3. And if we, when we try to take average, because we are trying to represent the whole length 1 meter, so mean load will be S1, sorry, S4 plus S3 by 2. So as S3 is more than S4, so their mean will be definitely more than S4. So that means we are getting little bit higher mean load, mean breaking strength. So in this way, if we go on breaking the load length 1 meter to smaller pieces and test the yarn in smaller gauge length, we will gradually get the higher gauge. So this phenomena is known as the weak link effect. Okay. So this has been discussed here. So S3 total length, if we take L, capital L, in that case the strength will be its weakest point, S3 will be the strength, and if we divide it to four equal parts, so then the mean strength will be S1 plus S2 plus S3, okay, divided by S1 plus S2 plus S3, or in this case in part 4 there will be another, say this is S4 divided by 4, which will be more than definitely S3. This has been explained here. For length L1, breaking strength will be S1. So this will be smaller L. L1 breaking strength is S1. So this has been explained here. So effectively what we have observed, that with the reduction in gauge length we get the increase in strength, effective strength or measured strength, and this is actually derived by the equation by Peirce that we will discuss. And irregularity also is important. Specimen length we have discussed. Now suppose we have two yarns. Yarn 1 has got this type of strength distribution, okay. Another yarn has got strength distribution shown by this green plot. Both of them, they are having the same mean strength, and that's why the effect of the weak link effect of length will be prominent in case of red yarn. That is, the higher the variability, higher will be the weak link effect. Now I will give you one ideal example. It will be clear. Suppose one yarn is having no variability, perfectly ideal yarn, okay, like as I told that, like any engineering material, so there is no variation, zero variation. And another yarn is having high normal yarn with a blue color. So blue color yarn, as we know, there is a weak link effect that we have already explained, but the yarn without any variation, zero variation, in that case, irrespective of the length, the strength will be same. So if we take different gauge length, strength will not change. So here weak link effect is not there. So with the increase that it shows, that with the increase in irregularity, the weak link effect also increases. So another yarn with higher variability, the weak link effect will be more prominent. Okay. So for more irregular yarn, the effect is hence by adjusting the gauge length, the test result may be changed. So standardization of gauge length is important. So for any standard procedure, gauge length is important. If we change the gauge length, the test result will change. So this we have discussed regular yarn and irregular yarn. The irregular yarn will have more weak link effect than regular yarn. Okay. And as I have mentioned, the empirical relationship proposed by Pierce is this, where SL equal to the strength at gauge length L. So this is the gauge length. Strength at gauge length L is the SL. Now if we increase the gauge length to R times of L, so this is if it is RL, R times of L, if we increase the gauge length to 2, double, so it R will be equal to 2. In that case, the strength will be SRL, and using the weak link effect, so if there is a weak link effect is there, so SL will be more than SR. Okay, and the relationship is SL minus SRL equal to 4.2 multiplied by 1 minus R to the power minus 1 by 5, that means minus 0.2. So R to the power minus 0.2, bracket close, and by standard deviation of yarn strength when we test with the gauge length L. So sigma L. This is the Pierce empirical relationship, and V here is the CV percent. If we consider the CV percent and replacing the CV percent from with the initial relationship, we get the modified relationship where V is the CV percent and CV percent equal to standard deviation by mean multiplied by 100. And this relationship we will be using to measure the strength at any gauge length. If we change the length, then we can calculate the change in strength. And from this relationship, we have rearranged the equation. From this relationship, we can see if we increase the R, that means if we increase the gauge length, that means SRL will reduce. That means strength at that gauge length will reduce. So which will, and SL is constant because of the initial strength. So the ratio will reduce. And also for more variable yarn, that is V is CV percent is more, higher variability, again the strength will reduce at SRL. So SRL will reduce, that effect will be more, that weak link effect will be more. Okay. Next is the rate of loading. So rate of loading will also affect the strain and time to break. So suppose one yarn of length L, we are extending it to a rate E1. So this is a fixed jaw, J1 is the fixed jaw, top jaw, and jaw 2 in tensile textile we are moving it at certain speed, that is at E1 rate, E1 millimeter per minute speed, rate of elongation. And with the same yarn, if we change the elongation rate to E2 millimeter per minute, so where E2 is more than E1, so that will affect the strength of the yarn. So to understand this effect, let us see that the viscoelastic model. So this effect is basically due to the viscoelastic effect, viscoelastic nature of the material. So textile materials show an increase in breaking strength with the increasing rate of extension. Okay, with increasing rate of extension with a decrease in extension, that we will discuss. So time to break will reduce. So due to viscoelastic nature of textile material, they require certain time to respond to the applied stress. So the different types of textile materials, they respond differently depending on their structure. Now let us see. So textile material is generally, it's a viscoelastic model, viscoelastic in nature. So it has got viscous component and elastic component. The viscous component is denoted by dash pot, and spring component, that elastic component, is denoted by spring. So this is the simplest model. Okay. Now for spring, in case of spring, the load applied is proportional to the extension. So if we extend the material, the resistance, this is the force, means it's a resistance by the material. So force is proportional to extension. Here F1 equal to K1 multiplied by extension, where K1 is the spring constant. And in case of dash pot, the force or resistance is proportional to the rate of extension. It's not the extension, it's a rate of extension. Okay, and K2 here is the dash pot constant. Now we can see, if we increase the rate of extension, then due to increase in rate, so due to the dash pot component, the material will impart more resistance. Okay, that means it will resist more. But for 100% elastic material, springy material, which will represent by spring, then with the extension, rate of extension, the strength will not change for 100% elastic material. But our most of the materials available are viscoelastic in nature. That's why with the increase in rate of extension, the force required will be more. Like we can see this from this curve. At lower rate of extension represented by blue color, the load stress is lower than the higher rate of extension, and this is again expressed by empirical equation where Ft is the breaking load at the extension where time to break is T. So you are keeping the rate of extension in such a fashion, the time to break is T, and F10 is the reference load where time to break is 10 seconds. And if we try to rearrange this equation, we will get Ft by F10 equal to 1.1 plus 0.1 minus 0.1 log T, and that means 1 plus 0.1 log 10 means 1, so minus log T, and we can rearrange it further. Ft minus F10 by F10 equal to 0.1 log 10 by T. Now where if time required to break is T is more than 10 seconds, then our strength at time T for time to break T second will be less than F10. That means if we stretch the material, if we extend the material at slower rate, we will get the breaking load lower than the case where we are actually extending it at the higher rate. Now this equation Ft minus F10 by F10, this equation if we generalize further, instead of 10 seconds, if we consider any other reference time which is h second, then the general relationship will be Ft minus Fs by Fs equal to 0.1 log S by T, and if we want to measure the percent change in breaking load, that means Fs was the initial standard breaking load with a standard time, and when we increase the speed, so we have got the higher load and by Fs and multiplied by 100. That means this is showing the percent change in breaking load when we change the speed of extension. So we'll do few numericals based on all these concepts, how the breaking load changes when we change the rate of extension or when we change the gauge length. And as per the British standard, the time to break the specimen has been specified as 20 plus minus 3 seconds. Only for this is only for CRL type machine, constant rate of loading type machine, not for CRT type. Then capacity of machine, that we have already discussed. Machine with very high capacity, if we try to test a very fine material like a tensile tester, which is with a very high capacity of load, so it's like 1 ton, which is for thick rope. In that machine, if we try to test a single fiber, the time to break will be very short and we may get optimistic result. Also, the break of the specimen should not be at the extreme of the instrument capacity. Like suppose a machine is maximum capacity is say 10 Newton is the maximum load. So we should not test the material which is nearly say 9.99 Newton. That much strong yarn we should not use. So it should not be close to the extreme capacity of the instrument. Previous history also changes the tensile characteristics of the same material. Okay, like a cotton yarn. Okay, so one of fresh cotton yarn and another cotton yarn is kept for long time for weathering. So the weathering will degrade the yarn and the strength will be different. Similarly, for different chemical treatment also changes the characteristics. Here this picture shows the scoured fabric, and when we are treating with different chemical at different concentration, the load elongation behavior of the same material gets changed. Humidity and temperature, that we have already discussed. As the humidity changes for cotton, the strength will increase. For other fibers, the strength will reduce. Most of the other fibers, the strength reduces. So the temperature, although it has not much effect, but at very low temperature the fibers may be brittle and it will change its stress strain characteristics. And clamping also, for same material, if we clamp improperly, then the result will be different. Like as I have mentioned earlier, for this is the standard stress strain behavior, and if we clamp loosely, there is a jaw slippage, the stress strain behavior will be like this. Okay, so we have to follow proper procedure, and if we clamp it at too high pressure, there will be jaw breakage, the jaw damage. Now, this aspect we will discuss in the next session. Thank you.